Hi everyone, my name is Saurabh and I'm the founder of Exa Protocol. And in this video, I'm going to discuss about the research at Exa, specifically the elephant in the room or the yellow paper that we have written. And I'm going to talk about what the paper says, introduction to our Darwin blockchain, the layer one. Talking about the calculations we have done in the yellow paper itself, how we came up with the TPS of what we are saying, and it would be a great learning experience for everyone. So let's get started. So we are calling our blockchain as Darwin, and we say that it is a scalable and a fast mobile-first blockchain. And the version of the paper that I'm going to discuss was published last year in November. And there are a few updates in this paper, but more or less the crux of what we are building is still the same. We have published this paper on the website itself. You can go through it. There is this table of contents, and you can figure out specifically what you want to look at. Specifically in this video, I wanted to discuss what Exa protocol is doing to build this layer one. So in this paper, we have mentioned that Darwin is a scalable and fast mobile first blockchain that achieves a theoretical maximum of 22 million transactions per second at scale. So of course there is a star to it. When I say something at scale, so I'm saying if the network grows and it grows beyond, let's say 500 million to a billion nodes, billion mobile nodes, then our network automatically scales and we can hit a TPS of 22 million. Of course, everything stemmed from the idea, what Satoshi Nakamoto, when he first published the white paper, everything began from that. The thing that we have built, a mobile first layer one that runs natively on mobile devices, it is built for the next 2.5 billion people who do not own a PC. I'm specifically talking about the folks in Southeast Asian countries who just have a phone, who do not know how to operate a PC, or let alone write a terminal command and run a client. Now, when we started building Darwin, we had this thing in mind that mobiles are the hero and they can run a full-blown blockchain client, given the let's say a POS consensus or a POW consensus. We have stemmed everything from that idea, and what we have in mind is that a mobile of today is as capable as a PC from just 2 to 3 years ago. In this version of the chain that we have built, we are introducing two types of nodes in the network. First is a mobile node that can mine the transaction block. It's a regular block that every layer one has, that contains a list of all the transactions that have happened. And we are also introducing a second node, which is called a server node. So a server node does not take part in the transaction validation process. However, the server nodes are required to keep the entire Darwin tree, the entire Darwin chain as a cold storage. With this chain, we have introduced a ton of new concepts. It's not about we cloned Ethereum or we cloned Bitcoin, but there are a ton of different concepts that we've introduced. Let's in this third section, called terminology, we have mentioned all the new terms that we have introduced. Let's touch upon a few specific terms that are important for understanding, and of course you can look at the paper and you can read other ones as well. So first is the nodes that the term node. When we say node in our paper, we are specifically talking about the mobile devices. And since Darwin has multiple parallel chains, and every child chain has a parent chain, and so forth, we have defined that as well, what a parent chain means. So a parent chain is the one that has children in the future. We have server nodes. A server is basically a heavy computation device. It could be someone running a big PC or even running a server farm. So that's what a server node is. A Genesis chain is the first chain in the Darwin network, from which everything stems from. Talking about chain velocity, that's also an important concept. It is basically a measure of what the TPS of the chain is, and we use this chain velocity to determine how many child nodes will be created from the current chain that is about to terminate. We have Genesis block. We have given it a special symbol, which is FB star. So Genesis block is the first block of the entire Darwin chain. This is where everything begins from. Transaction blocks, it blocks all the transactions that are there between the nodes. We have audit blocks. So the audit blocks, these are mined by the server nodes. So the server nodes, what they do is, it's more or less like they go to the chain. They go to a particular child chain and inspect like what all the transaction blocks have been added so far. And the frequency is such that after, let's say, 10 transaction block, or an audit block is added by the server nodes. So the audit block basically verifies the previous 10 transaction blocks. We have fossil block. So fossil block is a special Genesis block. So a Genesis block of any child chain of that has come up from the parent chain has the first block, which is called a fossil block, and it contains all the log of the previous parent chain, what all wallets were there, what's the summary of the previous chain basically. We are using proof of stake consensus, and I guess that's all. We'll discuss all these terms like the NWC, how many wallets can be allowed in per chain in future. That will make more sense when we start discussing the later chapters. Now, all so far, I'm talking about a parent chain and a child chain. Of course, it can be a bit confusing. So here, how the network really looks like. So if you look at over here, you will see, if you forget about the other aspect of the network, you will just see that it is basically a linear chain, right? If you just look at the current thing that I'm showing you, it starts from the Genesis block, then we have the transaction block. So transaction blocks basically contain all the transactions that have occurred between the nodes, and then after some time an audit block is added, and if the time is right, if the conditions are right, the chain may mutate. So when we say the chain is about to mutate, it means that it will split into two, and whenever the chain splits into two new fossil blocks are created, or 8 more fossil blocks are created, depending on how many child chains we have created. So the fossil block will contain the summary of the previous child chain. So the previous parent chain. So this parent chain, this fossil block will have that information. This one and this one, both of them will have this information of the previous chain. And these fossil block will also have information about what all wallets or the nodes were migrated to this chain and to this chain, right? So these fossil block contain that information. Now if we look ahead, you will see that it against this part of the chain, what we call as a child chain, is basically another linear chain. Again, it proceeds as normal. The transaction blocks are added, then audit blocks are added, and again, if the condition is right, it mutates again, and it can go beyond just one chain to maybe 2 chains or maybe 4 chains. We'll discuss in the future. And this is how the network grows over time. It if the need arises, it splits and then accommodates more wallets. So this splitting event, we call it mutation, is basically an event that splits the active child chain into multiple child chains depending upon the chain velocity, like I mentioned before. So what mutation event does is it distributes the wallet between the new child chains in such a manner that the TPS of subsequent chains is divided equally. We don't want the network to grow in a non-equal manner. Like one part of the chain may grow in very fast, and the other one may not grow that well. That will create an unbalanced tree. So we distribute the wallet in such a manner that the child or the child chains, they grow equally in the future. And we have made sure that the minimum number of nodes in one child chain before mutation is 256. If that condition is not met, then the mutation will not happen. Now, what we are also talking about here is the mutation event is governed by a splitting factor also, which is called lambda star. So it is again a function of the total number of wallets in the parent chain, the total active wallets in the chain, and we have defined how the splitting will take place based on this parameter. Um, let's talk about the how, let's say, if you are in one child chain, and if that node wishes to relocate to other chain. Let's say you are in Canada, and somehow you go to Europe, but you are still in a child chain that is more or less concentrated, more or less has nodes that are concentrated in Canada. So you will your client will see that the average latency between all the other nodes in your particular child chain has increased a lot, and it will again ping the other child chains in the network to figure out which is the best one for me now, and it will automatically migrate you to the next chain again, or to automatically optimize the network. So it can happen that you are currently in one child chain, and then your client decides that maybe this chain is not suited for me given the conditions, and it can hop between the nodes in order to optimize the network latency. So this is what the relocation of nodes here is in this section. Now let's talk about one particular attack that everyone has intensively read about, is the 51% attack on a distributed network. So with Darwin, we have architectured it in such a way that that 51% of attack by means of Sybil attack is practically impossible. So let's take a situation where there are 10,000 child chains in the network, and there are around 3,000 mobile nodes in one child chain. So this will mean that there are about 30 million active mobile nodes in the network. Now it can appear that the attacker only needs to spool 3,000 mobile nodes to take over a child chain, but again, this is not possible because whenever a new node is available to join the Darwin network, it is randomly assigned a child chain. So the probability that all the 3,000 nodes will join one particular child chain is quite low. So how low we are talking about? First of all, a probability that this new node will join one particular child chain that the attacker wishes to attack is 1 divided by 10,000, which is defined over here. So this is the probability for a node to join one particular child chain. Now if the attacker has spooled, let's say, 3,000 of those mobile nodes, and they all wish to join that particular child chain, this is already quite low. So if you do the math, if you just look at the numbers, this is practically impossible for any attacker to attack the network, even if all the child chains have limited number of mobile nodes. Now let's talk about the chain performance. We started off by saying that Darwin achieves quite a high transaction per second throughput, and let's see how we have actually come up with that. What's the math behind? So we have architectured Darwin in a way that every child chain has a TPS of 142. So let's first have a calculation of how this 142 number popped up, and how we are saying that this will scale. So we are saying that at peak performance, the mobile nodes propose the creation of a transaction block using POS consensus every 1 second. So every second a block can be added to the chain or to a particular child chain, right? So whenever I'm saying child here, chain here, it is the child chain. So in that particular child chain, a block can be added every second at peak performance. So, and after approximately 10 transaction block, an audit block has to be created by the server node. So the audit block, like I mentioned before, it basically audits the previous transaction block, and it is required. So after approximately 10 transaction blocks, an audit block is added, and the audit block has a block time of 60 seconds. So it will take approximately 60 seconds to mine this audit block. The performance is set as such. At peak, the number of transaction per block can be 1,000. The peak transaction block time is 1 second, and the peak transaction audit block time is 60 seconds. Now again, like when we talk about the peak performance of any child chain, the chains in the Darwin network follow a block pattern of 10 transaction block for every audit block. which is then, like I have showed over here, what it will look like. 10 transaction blocks followed by an audit block. So this block pattern will be followed at peak. So we can say the total time taken by this pattern, this pattern of 10 transaction block and one audit block at peak, is basically 10 times the transaction block time, and 1 in times the audit block time, right? So since we know that the audit block time is 60 seconds and the transaction block time is 1 second, it gives us a segment, the time to create this segment of the chain to be around 70 seconds. Therefore, for a 10-minute interval, now let's do even more. Let's average it out, right? So therefore, for a 10-minute interval or a 600-second time frame, there will be approximately 600 divided by 70, which is 8 segments. So we'll see 8 of these patterns in a matter of 10 minutes. 8 of these patterns in a matter of 10 minutes. So now let's do some math for the TPS of a child chain over a period of 10 minutes. So the total transaction blocks added would be 10 times the number of patterns we saw. So we'll see an approximately 85.71 transaction blocks in a matter of 10 minutes at peak. So total transaction would be 1000 times this number, which is 85,710. And if we do the TPS calculation, we'll see it comes out to be around 142.85 TPS at peak performance. Now let's talk about the performance of the entire network. Now, when the Darwin chain is mutating, it can mutate up to from 2 to anywhere between 2 to 8 child chains. From one parent chain, there could be 8 child chains in the future. But for the sake of simplicity of calculations, let's say that the number of the Darwin chain is splitting evenly, and the split is binary all throughout the chain. So over here we have done a math to figure out how many active child chains will be there when a billion mobile nodes are there on the Darwin network. So we have defined a new parameter over here, which is lambda n, which is called which defines the total number of active child chains in the network. Now if you look at it over here, we have a relationship between the total number of mobile nodes and total number of active child chains that there are. So if you look at the math, the total number of wallets in one chain multiplied by the total number of active child chains should come out to be a billion. Again, this is theoretical maximum. We are assuming that all of the child chains are saturated and have 6400 mobile nodes. Of course, this number can vary, but for the sake of simplicity, we are just taking this assumption. So which means that at scale there will be about 156,000 child chains active in the network. Now, since all of the chains work independently, the total TPS of the Darwin network, again, this is a theoretical maximum, would be 156,000 times 142, which gives the TPS for the Darwin network to be around 22 million TPS. Now, if we do calculations and bring in the network latency of, let's say, 20 milliseconds per transaction in the network, we see that it is theoretically possible that the TPS of the Darwin network can be 7.8 million TPS again at scale. So this was the calculation behind how we are saying that the Darwin is 22 million or 7.8 million TPS, theoretically maximum at scale. Now, when we were building this chain, all of the layer ones, they were relying solely on single type of blocks, which is transaction block in R terms. However, in a Darwin chain, a typical chain looks like this, like we have shown. It starts from the genesis block, then the transaction blocks are added, and then the audit block is added after some time, and it can again mutate and create fossil blocks. So every child chain in Darwin begins with a fossil block, which contains the summary of the previous parent chain. And it also contains a summary of what all nodes were migrated from the parent chain to the current chain. As the transaction was created and added to the transaction blocks, a limit is reached at certain point when the chain becomes a bit too heavy for a mobile node to handle, and we have set that limit to about 50 megabytes. And when that condition occurs, a mutation event occurs, which is called the evolution process in Darwin also. The chain splits into, let's say, 2 or even more child chains to optimize the network. Now let's talk about the concept of chain velocity. So far we were discussing about the mutation event and how the chain splits after a certain point. It is governed by the chain velocity. The parameter that we are talking about is chain velocity. So the chain velocity is basically an average TPS of the chain from the fossil blocks to its mutation. Now, this factor predicts the number of child chains that will be created post the mutation event. So we have defined, what this is. So for a TPS, let's say a child chain has an average TPS of about 11 previously, then we can expect after the mutation the chain will split into 8. And if the chain velocity is between 0.36 and this and 11.5, the chain will split into 4 and 2 given for this condition. And there is a condition when the chain may not even split. So it will just basically renew the chain, and the mutation will just create a new child. The only one child will be created for that parent, what this means. And there is a possibility that the chain is so slow for its mutation that we call it dormant. So a dormant chain, it will progress very slowly, and we don't want that in the network. And so what we do is we terminate the chain, we migrate all the mobile nodes to other child chains that are near to that mobile node. And when I say near, I'm talking about the network latency that are near to my node. Now the mutation event is governed by the splitting factor called lambda star, which is a function of total number of transactions and total wallets in the child chain. So the lambda star is defined as such. It is a binary number between 1 and 0. So one value occurs when the total number of transactions exceed 250,000, or the total mobile nodes in the chain are approaching or exceeding 6400, and the total number of wallets or the mobile nodes are greater than 256. Otherwise, the value is 0. So numerically, like I mentioned, if it is 0, the chain will not split, and if the value is 1, the chain may split at the next audit block or at the point of next mutation. Now, lambda star is just an indicator whether the chain should split at the next audit block or not, at the next mutation or not. However, the decision to split the chain is also governed by chain velocity. Now, this is how both the parameters together work. Now, first of all, we'll look at the value of the lambda star, which is an indicator whether the chain should split or not. If the lambda star value is 1, then we'll look at the chain velocity. Now, if the chain velocity again is between the parameters that we have mentioned over here, let's say if the chain velocity is less than 0.022, it means that the chain is dormant, and then you mark the chain dormant and you take the necessary steps next and proceed. Again, we have mentioned what to do when the chain velocity is different. And however, if the lambda star value is 0, then your chain will not split. Let's talk about the different blocks in the Darwin network. In the section 10.1, we are talking about the types of block in the Darwin network, right? We see that it starts with the genesis block, then it goes to the transaction block, and then after some time an audit block is added, and then it may either proceed, or at the audit block a mutation event can happen and the fossil block is created for the next child chain. So let's talk about the genesis block, and we have given it an indicator FB star. So the genesis block is the first block of the Darwin chain. It is a special version of the fossil block where the body of the block is empty, right? The next is the transaction block, The transaction block stores all the the log of all the transactions, and they are bound by the mobile devices. And each transaction block can hold a transaction about 1,000 transactions at peak, and the block time for the transaction block varies from 1 second to 600 seconds, again depending upon the current network TPS and also the number of transactions currently pending. It depends on that. And the transaction block time varies according to mathematical functions which we haven't mentioned over here. But if you were to plot it, it will look something like this. If the total number of pending transaction in the block, let's say, approach 1,000, then the block time goes to a second. And if the pending transaction are, let's say, in the range of 50 seconds, then the block time would be, let's say, in minute or 3-minute time. The transaction block time can vary. And we have done this so that we don't create empty transaction block or transaction blocks that have less amount of transactions in those. And then there is an audit block. So the audit block is basically created to verify the previous transaction block. It is created by the server nodes, and the block time of the audit block is set to 60 seconds. It takes about 60 seconds to mine the audit block. And in the next sections, we have mentioned the architecture of the transaction blocks and also the audit blocks, if you go through the yellow paper. So yeah, I mean, this was an intro video of our yellow paper and also the Darwin blockchain that we are building. I hope this video gave you an idea of what our Darwin blockchain is and how it works. So thank you for watching this. We are of course coming up with some more research talks at EXA, and thank you so much.